now I will try to derive the expression for the other h terms, that is your h 211. Now, this h 211, that is I equals to 2, c and d they are equal to 1. So, j equals to maximum between your 212, 211. So, this is 2 to 2. So, there will be only one term. So, this is nothing but trace of like u j equals to 2, c d is 1 1, then comes your j 2, then comes your u j, j equals to 2 and your this particular I is also equal to your 2. So, u 2 2 transpose. So, this is the way you can find out the expression for this particular h 211. Similarly, h 212. So, that is nothing but, so once again 212, the maximum is 2. So, 2 to 2 there will be only one term, then comes your u, j is 2 here and c d 1 2, then comes your j 2, then u, j is nothing but equal to 2 and I is also equal to your 2. So, I is also equal to your 2 and I will be getting this particular the expression. Now, then comes your h 212, 212, that is nothing but once again. So, 212 maximum is 2, 2 to 2. So, I will be getting trace of u, j equals to 2 here, then c d 212, sorry. So, I am just trying to find out actually h 221. So, this is nothing but u. So, j equals to how much? J equals to 2 and c d is nothing but 2 1. Okay. Then comes your j 2, then comes u, j equals to 2 and I is equals to your 2, I is 2 here. So, this is the expression. Then comes your, I can also find out what is h 222. Now, this h 222, so here once again there will be only one term. So, is nothing but trace of u, then j equals to 2, then comes c d equals to 2 2, then j 2, then comes your u, j equals to 2 and I is also equal to 2 and transpose of that. So, this is the way actually we can find out the expression for h 211, h 212, h 221 and h 222. So, using this actually I can find out the expression for your the final expression for these particular the h terms. So, this is your h 211. So, this is the expression as we have already seen. Now, once again we know that this u 211, that is nothing but u 211 is nothing but actually partial derivative with respect to theta 1 of u 21. Okay. J 2 we know, u 22 transpose we know. So, these matrices we can multiply and we can find out the trace and the trace will become equal to this. So, this is nothing but the expression for your this h expression for h 211. Now, h 212. So, this is the expression and once again you can find out what is u 212, that is nothing but the partial derivative of u 21 with respect to theta 2. So, this is the expression. So, this is known, all the terms are known, and if you just multiply these three matrices and if you find out the trace of that, this will become equal to 0. So, what we do is, so we can find out this particular h term. Following the same method, we can find out what is h 221, okay, the same method, and we will be getting h 221 is equal to 0. Then comes your h 222. So, this is nothing but this particular expression which you have already derived, and here. So, this u 2 2 2 is nothing but the partial derivative of u 2 2 with respect to theta 2, and if you just find out. So, you will be getting this particular matrix, and the other matrices are also known. So, these 3 4 cross 4 matrices, if you multiply, take the trace value, you will be getting that is equal to 0. So, following this particular method, so we can find out actually your all the h values. So, the only thing which is left, if you see this particular expression for your tau 1 and tau 2. So, this is the expression for this tau 1 and tau 2. So, all such d terms, all the d terms, all the h terms, all 8 h terms we have determined. Only thing which is left is your C 1 and C 2. That means, your these two gravity terms are yet to be determined. Now, let us see how to determine. So, this particular the gravity term. Now, to determine the gravity terms, actually I am just going back to this particular expression, and let us try to find out the expression for C 1 and C 2 from here. So, this is C I. So, let me try to find out the expression for C 1. So, I equals to 1, that is j equals to what? 1 to 2. So, there will be 2 such term. So, I can write down like m minus m, j equals to 1 here, then comes g bar, then comes u, j equals to 1 here and I equals to 1, then comes your r 1 with respect to 1 bar. Then there is another term, that is your j equals to 2 now. So, m 2, then comes your g bar, then comes u, then j is equals to 2. So, it is 2 1. So, u 2 1, then comes your j equals to 2, that is 2 2 bar. Now, let us see how to determine, and I can also find out the expression for C 2 also. So, let me write down the expression for C 2 also. So, I equals to 2. So, j equals to 2 2 2. So, there will be only one term, that is minus your m 2 g bar, then comes u, then j equals to 2 and your I is also equal to 2, then comes your R 2 with respect to 2 bar. So, these are the expression for C 1 and C 2. Now, let us see how to derive further using this particular expression. So, how to derive further? Now, to derive further, actually let us see this particular C 1. So, exactly the same expression I got, whatever I wrote. So, this is actually your C 1. Now, here m 1 is the mass of this the first link, but g is the acceleration due to gravity. Now, here if you see, as we discussed, the g has 3 components like x, y and z component. Now, here actually the way the coordinate system has been considered, actually if you see the coordinate system, let us see the coordinate system once, we will understand. If you see the coordinate system, so this is actually the y direction. So, g is acting opposite to the y direction, vertically downward, and that is why actually here we will have to put. So, this particular expression 0 minus g, in place of y I have written minus g and z is 0, but here one extra 0 I have put, the reason I will tell you. Okay. Now, here this u 1 1 we have already determined, and this is nothing but a 4 cross 4 matrix. Okay. Then comes your this R 1 with respect to 1. How to determine R 1 with respect to 1? So, if I consider that this is my link 1, and for this particular link, supposing that the total length is nothing but L 1. Okay. So, its mass center is here, okay. And the coordinate system, as I told, because we are interested to determine how much will be the reaction torque. So, the coordinate system is attached here. Okay. So, with respect to this, so this is the x axis, with respect to this what will happen is your this will be minus L by 2. So, this is y and this is your z. So, this will be minus L by 2. So, here this R 1 with respect to 1 bar is nothing but the coordinate of the mass center, that is your minus L 1 by 2 0 0, that is y is 0, z is 0 corresponding to this particular point, and this 1 is actually just below the position vector we put 1. So, that particular the 1. Now, you check the dimension. So, U is having 4 cross 4 and this particular R 1 with respect to 1. So, it is having 1 cross 4, this is here there is a transpose. So, this will become your then 4 cross 1 matrix. So, this is a 4 cross 1 matrix and this is a 4 cross 4 matrix. So, if you multiply, ultimately I will be getting 1 4 cross 1 matrix. Now, this particular G matrix has to be 1 cross 4, otherwise we cannot multiply, and that is why actually we have made it 1 cross 4. So, this is nothing but the 1 cross 4. So, G has got 3 components and that is why this particular 0 has been added as an extra, okay, just to make it that particular 1 cross 4. So, this 1 cross 4 can be multiplied by this 4 cross 1. Okay. That is why, so this particular extra 0 has been considered here. Exactly in the same way, here also we can determine, the only thing is the expression of this U 2 1 is different and this R 2 with respect to 2 is nothing but this, because in place of link 1, now we will have to consider link 2. For this link 2, your mass center is minus L 2 by 2 0 0 1 transpose, and if you just put all such things here and multiply, then I will be getting the expression for C 1 and this is nothing but this one. So, this is the way we will be getting the expression for this particular the C 1. Now, let us see how to determine the expression of C 2 following the same method. C 2 expression I have already got, and exactly in the same way G has to be written. U 2 2 is known, R 2 with respect to 2. So, this is also known, and if you multiply, then I will be getting this your C 2, that is half m 2 G L 2 cos of theta 1 plus theta 2. So, this particular expression you will be getting for your this C 2, and once you have got this particular C 2. So, now we are in a position to write down the expression for this particular the joint torque. Okay. Now, in this particular expression, so these particular terms, if you just add them up, whatever we got, because all like 2 values of D, 4 values of H and 1 value of C we have got, if you just write them up and if you just arrange, then you will be getting this type of expression. So, this big expression multiplied by theta 1 double dot, that is you see 1/3 m 1 plus m 2 into L 1 square plus 1/3 m 2 L 2 square plus m 2 L 1 L 2 cos of theta 2 plus 1/4 r square into m 1 plus m 2, and you can see that all such terms are related to the mass, the length of the link and your mass and length of the link, and there could be some radius term here also, but here there is no radius term, but yes, radius term is there. So, these are all actually related to the geometry. Are you getting my point? The geometry, and this is nothing but the inertia term. These are all inertia terms multiplied by this theta 1 double dot. Similarly, So, these particular terms are multiplied by theta 2 double dot. Theta 2 double dot is nothing but angular acceleration of the second joint. Now, here once again you can see m 2 L 2, then comes L 1 and we have got r, that is your the radius of the second the link and or the first link. So, here the radius terms are also there. Okay. So, this is once again actually the inertia terms. Okay. Now, then comes your these particular terms like theta terms involving theta 1 dot, theta 2 dot, then theta 2 dot square. So, these are nothing but is your the Coriolis and centrifugal term sort of thing, and this particular part your cos theta, cos of theta 1 and theta 2, these are nothing but is your the gravity term. So, we have got inertia term. So, these up to this actually we have got the inertia term. So, these are nothing but the inertia terms. Then we have got your the Coriolis and the centrifugal term, and here. So, these terms are nothing but is your the gravity terms. And another observation we should have a look. You see, we are trying to find out the expression for the joint torque at joint 1. Okay. Now, here if you see carefully, there are a few terms related to your theta 2. For example, I have got cos theta 2, I have got theta 2 double dot, cos theta 2, then your theta 2 dot square, then cos of theta 1 and theta 2. That means, although we are trying to find out the joint torque, that is torque at joint 1, the second joint angle has got some contributions towards this particular the tau 1. Now, we are just going to see the expression for the second joint term, that is your. So, these particular terms will be nothing but the inertia terms like 1/3 m 2 L 2 square plus 1/4 m 2 r square plus half m 2 L 1 L 2 cos theta 2 into theta 1 double dot plus 1/3 m 2 L 2 square plus 1/4 m 2 r square theta 2 double dot. So, these are all inertia terms. Okay. So, this is multiplied by theta 1 double dot, this is multiplied by theta 2 double dot, and then we have got actually your another term here. So, we can see. So, this term is actually the centrifugal term involving theta 1 dot square, and we have got the gravity terms. Okay. So, this particular expression for theta 2 once again contains 3 terms, and once again if we look into this, we are trying to find out the expression for the joint torque, that is theta that is tau 2, and here this theta 1 double dot has got significant contribution. Then here we have got cos of theta 1 plus theta 2. So, theta 1 has got significant contribution on the joint torque 2, and that is why actually these particular the contributions are coupled contribution, and due to this particular coupled contribution, the better way should be to determine this particular joint torque, like to consider the multiplicity dynamics and show that the coupling terms we can consider very efficiently, and you will be getting very good expression for this particular tau 1 and tau 2. But this particular method, the method which I have discussed, it has got one advantage I should say, because if you use this particular method, there is a possibility that you will be getting very structured form of this particular expression for the joint torque, and which may not be available in other method, but this method gives very structured form. Now, another thing I am just going to mention, like if I consider the slender link, that means your for slender link. So, slender link your L is very large compared to your R. So, the terms involving R square are small. So, those terms actually we can neglect. For example, from this particular the expression here there is one R square term. Okay. So, this particular term you can neglect and it will tend to 0 if you consider the slender link. Similarly, here there is another R square term. So, this will also tend to 0 if you consider the slender link, okay, and the expression for tau 1 will become simpler. But here you will not find any such terms involving R or that type of thing. So, this is the way we can make it simple by considering that the links are slender. Similarly, here if you consider the slender link, so this term will tend to 0. Similarly, here there is another term who will become equal to 0. So, the expression for this particular tau 1 and tau 2 will become simpler. Now, in robotics actually what we do at each of the robotic joint, we just put the DC motor and the motor is going to provide this particular torque. Okay. And this particular torque has to be this torque is going to generate the joint angle and we will have to very accurately generate that particular the joint angle. Now, how to generate that very accurate joint angle, that I will be discussing after some time while discussing the control scheme. Now, here this particular once you have got the variation of this torque as a function of time, now we can think about what should be the power requirement for a particular joint, and if you know the power requirement, so we can specify, we can prepare the specification of the motor which we are going to put at that particular the robotic joint, so that the robotic joint will be able to provide that particular torque and it will be able to generate that particular the rotation very smoothly. Thank you.